Hi, I'm Leonidas. Welcome to this developer spotlight. I'm going to show you today how we created Solar Stage. That's a metaverse demo made with Uranus tools for PlayCanvas. You can already give this demo a try in your own browser by visiting this URL. Here are some screenshots from the demo. Before we take a look at how we built this demo, let me give you some info about me. I've been working with WebGL and PlayCanvas since 2012-2013. Seeing the PlayCanvas editor for the first time, that was a wow moment for me. I was looking through many WebGL frameworks and libraries, and my first touch with PlayCanvas and the editor was something big for my work and what I was looking to do. Since then, I've been working full-time with PlayCanvas for close to a decade. I have a master at civil engineering. I worked for several years in construction works. I turned my hobby at some point, that was coding, into a full-time job. Initially, I started as a web developer. I was building traditional websites using content management systems, PHP, Node.js, and other libraries. But my real passion was always real-time 3D rendering. My first attempts were doing architectural visualization, and that was using Unity. Throwing in Unity was great. Both the editor and the runtime was quite good, but the clients required accessibility. What if we run these visualizations in a web page? What if we integrate them in regular websites and make them accessible to any device? And that was PlayCanvas when it came to the rescue. And ultimately, myself, I learned game development through PlayCanvas. Let's see some of the projects that I first worked on. This was Animate. It was a Sketchfab-like portal. That was my first PlayCanvas contract. You were able to load your own models, set up your scene with lighting, colors, animations, and you could share these scenes with your friends by using a simple URL. It was quite a great project by the time. Then I worked on DuckTales avatar creator. That was for Disney, or a Disney TV series, made with PlayCanvas, of course. Then this was the recreation of the Linux library. That was an art museum that existed 2 centuries ago. Doesn't exist right now. So we recreated the exact experience based on old photographs, and we placed each frame, each picture at the same spot. And this is a 3D view, and you are able to click on the frames and see information about these pictures. Then I worked and created with my company the PlayCanvas asset store. That was the first PlayCanvas extensions marketplace. You could find useful editor extensions, tools, starter kits to bootstrap your PlayCanvas creation pipeline. And this was 2 years ago. We started working with my company in Aritelia. That's a procedurally generated open world social game. Which is still in development. We're still working on it. Our goal was to create an open world experience with AAA graphics right side in a web page. We're getting close to that. We're very excited working on this project. Now, let's talk about how we made this demo. The Solar Stage demo. Originally, it was made in Unreal Engine 4. The scene that you see here included dynamic lights, shadows, reflections, and all the goodies that you get when you publish projects with Unreal Engine. The screens that you see inside this 3D scene can play back video files MP4s directly on 3D surfaces, and the scene included high-quality PBR textures. Now, before we delve on this, let's talk a bit about why PlayCanvas over Unreal. Of course, this is not an apples-to-apples comparison. The main reason was to make it more accessible and shareable through the web. PlayCanvas builds require almost very, very short download times. There is no installation involved. PlayCanvas builds are easily shareable, both development builds and production builds. PlayCanvas is optimized to run on older phones. That was quite important for this experience. And of course, it makes it easy to integrate with other JavaScript libraries and frameworks. It works like any other web-based application, so the whole JavaScript ecosystem is accessible through your PlayCanvas application. The main challenges in moving this scene from Unreal to PlayCanvas, initially it was transferring the assets and the scene, taking all the models, materials, textures out from Unreal and into PlayCanvas. We had to reduce the resources size to make the download times meaningful for the web, reduce the memory allocation so it can run on older devices, mobile devices that have strict video memory limits. We had to implement a number of effects to get the same or at least similar render quality with Unreal Engine, and make several performance optimizations to avoid low frame rates. Let's take a look at each challenge and how we worked to make it meaningful and possible in PlayCanvas to run this scene. Here you can see the original scene in Unreal Engine. This is a scene that you can find in the Unreal Engine marketplace. It includes a number of models, high quality textures, great setup with effects and all the goodies that you get. How can we export this scene from Unreal to PlayCanvas? There is a great plugin in the Unreal Engine which is called GLTF Exporter, and you can use to get not only the models, the meshes, but also materials and textures directly inside a single file. That is the GLB or GLTF file type. Potentially you can get also the lights and the cameras, but these are not supported right now when you import this file in PlayCanvas. Now, how do you use this GLTF exporter in Unreal? First of all, you need to enable the plugin in the Unreal editor. When you do that, make sure to reload your editor so the plugin gets enabled in your project. Then select all of your static mesh actors in the Unreal outliner. And as a final step, go to File and Export Selected. You will get a big number of options to tweak and perfect your export. Some of the important ones are the selection of the material channels that you want to export. Here you can see in this screenshot a common selection that we do when we export Unreal scenes to PlayCanvas. That includes base color and opacity, normal maps. Optionally, you can export ambient occlusion if you use static ambient occlusion in Unreal. And of course, metallic, roughness, and emissive color. You can set the texture export resolution. The best setting here is JPEG if there is no alpha. And set normal maps to use no lossy image format. Now, this will make sure that your normal maps are exported to PNG. That's a lossless file format, which is quite important for normal maps. And also, if there is any texture that includes alpha, for example, you can get base color diffuse maps, and on alpha you can get the opacity sampler, then that texture will get exported to PNG to retain the alpha channel. So these settings are quite important. And as soon as you do that, it may take a while, you get the GLTF together with the texture maps and materials, and usually we import this in Blender before we go with PlayCanvas. And here you can see the scene imported in Blender. We do that importing in Blender to prepare the scene with a number of actions that some are optional, but it's very good to prepare your model before importing in PlayCanvas. That will be clean and delete any unused nodes. Sometimes you may select like a post effect node in Unreal, and then you get that in your final GLTF file. If you don't require this specific node, then remove it. It makes for a smaller file type and less entities imported in PlayCanvas. We also add empty nodes to better organize the hierarchy. Sometimes if you have too many actors in Unreal, and these actors may create a flat list of entities, and it's not easy to pinpoint where specific nodes or entities are. So usually we group these nodes in Blender in meaningful categories. For example, we may group walls, ceiling, and floor on a single category. Then we may have props or lights, meshes for the lights, and so it's very easy then to find them in PlayCanvas if we do that in Blender. If we are using LODs, that's a level of details, we'll talk a bit about it later. Then we add suffixes like underscore LOD0 or underscore LOD1 to meshes where it's required. And also we add local texture file references. You can Google that to find how that works in Blender. If you do that, then it's very easy to include not only the materials, but also the textures at the right material channels with your final FPX. And that makes it super easy to import the FPX in PlayCanvas and get both materials and textures uploaded in a single action. And that's it. And then we export to FPX, not to GLTF again, because PlayCanvas doesn't support GLTF import in the editor right now. So select export to FPX, and one important setting right now is to select on the path mode property the value copy, and make sure to select embed textures to tick that button. That will make sure that any textures referenced in materials will be included in the final FPX model. And voila, here it is. This is the Unreal scene imported in PlayCanvas, and it was actually quite easy to do so. We got the hierarchy here, cleaned up as we did in Blender, materials and textures, and it's almost done. Some final steps that you need to do to make sure that this looks right. One thing is lights are not imported inside the FPX, so we hand place them inside the PlayCanvas editor. That will be spotlights, point lights, directional lights, any lights used in the original scene. We update the materials with the right channel mappings. That doesn't happen automatically. So for example, if you have your metallic map in the blue channel, then you need to set this manually in the respective materials. Same with glossiness maps and opacity maps, emissive maps, any map that needs specific color channel instead of the default RGB. At the same time, we set blending in any materials that use opacity and require a blend type. And at the end, we play with the scene exposure and tone mapping to try to match the Unreal settings. That's easy in the PlayCanvas project settings. As soon as we do that, we notice that in Unreal we had 4K texture maps. That's okay, but when you're on the web and you want short download times, or when you want to run your application in low-end devices like older phones, then it may make sense to reduce your texture maps. How do you decide on the resolution? That usually depends on the size, the maximum size of the surface that this texture is used on that will occupy on your viewport. So we take it from there. For example, if we see a texture like a large wall occupying almost the whole viewport, then we decide this is going to be 2K, something like that. For smaller surfaces, we go to 1K or even less. We reduce the resolution size, and then we also apply basis texture compression. That's quite important because otherwise, with a lot of textures and these file sizes, these texture resolutions, you may run out of video memory that will be on iOS first and other mobile devices. At the same moment, sometimes we reduce the model poly count. This was not required for this scene, but we do that in the step where we import the model in Blender before importing it in PlayCanvas. We use the decimate modifier in Blender to reduce complexity in some models if it's required. And as a last step, we invert the roughness maps. PlayCanvas uses glossiness. So basically, glossiness is the opposite of roughness. From game engine to game engine, sometimes these channels are inverted. So in this case, if you get roughness maps, which is the case when you export scenes from Unreal, then invert them in Photoshop or any other image editor, so they are used for glossiness. Of course, if you are an advanced user and you don't care about adding another shader to your program, you can do so with a single GLSL shader command. Now, let's take a look at how we try to match, the final effects and image quality that we got from Unreal to PlayCanvas. One of the biggest things this scene used in Unreal and made it look pretty was real-time reflections. The original demo used screen space reflections, which are quite good because they can be easily seen on any surface. And they don't really require any special setup, but in our case they're too heavy on mobile, and also they are not available right now in PlayCanvas. Instead, we used planar reflections for the floor. In the Uranus Tools SDK, we have a very easy to use script that can enable planar reflections on any surface. And we also use box reflections for rendering other types of similar reflections on other types of surfaces, like vertical surfaces or the ceiling. And we do so in a larger interval. So we don't render those reflections per frame because it's too heavy and it may kill performance. For planar reflections, we use this script included in Uranus Tools SDK. We can set which entities are reflected to control performance and not have every small prop cast a reflection, because then we get double the poly count and double the draw calls in some cases. So we add a single layer. In this case, we call it water reflection. So we can control exactly which model and render components cast reflections. Reflections are rendered using an inverted secondary camera that is created in code by this script. And also we control which materials are going to have reflections rendered in their shader. So basically that's how we control which surfaces are going to have reflections. In this case, it's the floor. A similar script is used to render a cube map for box reflections. We can set the update frequency to have these reflections render only once every 10 frames, or even less, because this helps us optimize and have good performance with this type of effects, even on mobile. We can set the render width of the cube map, the resolution of the texture, also which layers are included in this cube map, so we can control exactly what's rendered in these reflections. And at the end also we set the surfaces that are going to have these reflections added by referencing the materials that we want to have box reflections added. This script is very similar to the PlayCanvas engine demo that shows how box reflections are used. You can take a look at that in the PlayCanvas repository. One of the most important things with this demo is the number of dynamic lights that are included in the scene. I think there are about 30 or even more point and spotlights in the original Unreal scene. In PlayCanvas we added 30 dynamic point and spotlights. And here we use one of the most important features that PlayCanvas has released recently, that is cluster lights, because otherwise there is no chance you can have that many dynamic point and spotlights in your scene. I would say that the maximum normally is 2 or 3 at the same moment, but in this case we have 30, which are rendered on runtime. They cast lights, and some of them even cast shadows. It works great even on mobile. Now, real-time shadows, that's what makes this scene so nice, because it creates contrast with the light, and actually it's very realistic to have all these shadows. Usually, if you are not careful about how you treat your shadows, your real-time shadows, you can get a dramatic performance reduction and very low frame rate. The main reason is that shadows require re-rendering the scene from the perspective of where the light is positioned. So basically each light can double the number of draw calls required to render this scene. In our case, we set only some spotlights to render shadows, and we used a very special script that Realtime Tools SDK provides and allows you to set the interval of how often these shadow maps are updated. So that can happen either per frame, once every 10 frame, or once every second. You have full control over both directional lights and their cascades, and for point and spotlights. This is great. You can have dynamic shadows and for many lights at the same moment. This is the screens that the original demo provided that render video files. So basically you have MP4s playing and updating textures, materials and texture maps directly on 3D surfaces. We use a variation of the original PlayCanvas video example in Realtime Tools SDK that can make this easy and also enable reflections and render everything directly on this 3D surface. And also video streaming is supported using a cloud provider like Agora. So basically on these screens, you can have your web camera connected and see your face, or you can even screen share your desktop and showcase stuff. At the end, to match this unreal rendering quality, we enabled a number of post effects. Most of these are found in the PlayCanvas engine repository, like screen space, ambient occlusion. It's quite important, although we disable this on mobile because it's a heavy post effect, but it can give depth on 3D surfaces. Bloom, to enable a lot of contrast between light and dark spots in the scene. Chromatic aberration, it's an effect that on the edges of your display makes the pixels distort in a way that mimics photography lenses. Sharpen, we barely use this, but we saw that in this specific scene, because there are so many different colors in the pixels, it can help highlight the edges of the geometry, and FXAA to reduce anti-alias. We also use brightness and contrast. PlayCanvas provides a post effect for that, but we don't use this in our case. We try to avoid using too many post effects because it can kill performance on mobile. So instead we have in Realtime Tools SDK a script that can do the same thing, basically allow you to set global brightness and contrast values per material. So it injects the required shader values at the global shader chunks like this. So before any material generates its shader, we modify the base pixel shader and the end pixel shader, so our own shader code is included with all materials. And in that way, we have control over the final brightness and contrast pixel value that each material in this scene uses. So basically it's like a post effect without using a post effect, which is quite cool because we get good performance. You can do very nice effects using this system. Just make sure to modify these values, the global pc.shader chunks values, before your materials compile. So add this script, let's say, at the root entity of your scene hierarchy. That way you can guarantee that it's going to be executed first. Let's go now to how we optimize performance. The first thing that you need to do is manage your draw calls. In this scene, we had too many draw calls. I would say that it was, 250. That is prior enabling shadows and reflections. That's too many draw calls. That's too many. We use hardware instancing to reduce the draw calls. PlayCanvas supports batching as well. It's a different technique. There are some limitations. For example, it may not work that well with LODs. It's not easy to disable and enable models on demand. In this case, we have an auto instancer. It's a very powerful plug-and-play script that you can use from the Realtime Tools SDK. You can import it in any PlayCanvas scene, and it will automatically find and manage your draw calls. It will reduce the amount of draw calls required to render your scene at the minimum number. So the way it works is hardware instancing is an extension that the GPU features, and it can be used to group similar models. Similar means models that use the same mesh polygons and the same material. So for example, if you have 10 entities that use the same model and material, those 10 entities can, instead of passing all these 10 objects to the GPU, like 10 different models, 10 different materials, instead we pass the model and the material a single time. That's one draw call. And we also pass in a supplementary buffer the position, rotation, and scale of each object. And then we instruct the GPU, hey, this is not a single draw call, it's 10 different draw calls. So that's hardware instancing in action. It's quite powerful concept, and PlayCanvas supports it. You just need to code your solution on top of it. With all effects enabled, the effects that we've seen before, reflections and shadows, the scene usually renders at around 100-120 draw calls. That's a big win. It comes from exercising exact control over when your draw calls are pushed to the GPU. So in this case, for example, we don't push all the shadows draw calls per frame. We only do it once every 10 frames, for example. Same with reflections. That way, the average number of draw calls that we push is reduced. And this way, we can get a very good frame rate, even with a complex scene like this. Luckily, this scene didn't feature too many polygons. That can be quite a problem sometimes with unreal scenes imported to PlayCanvas, but in this case, we didn't have to use level of details, LODs. LODs are basically different variations of the same model. So you have your model that may have, 10K triangles, and then in your modeling application, you create variations and you reduce the number of triangles. For example, LOD1 may have half the polygons. LOD2 only a few hundreds of these polygons. And then in a game engine, we use these LODs and we select the right variation of this model based on its distance from the camera. So if the model is close to the camera, we show LOD 0. If it is far, far away, we show the last LOD, because you cannot really tell the lack of detail from that kind of distance. In some cases, we don't even render regular polygons for this model. We only render a billboard. That's like a photograph of this LOD that we see from a distance. That's common with vegetation, like trees. You may tell when playing a video game from a distance, observe the trees. In some cases, they're only billboards. Another optimization that we have to do was, at some point, we added multiplayer support on this demo. So basically, we could have multiple avatars at the same moment rendering. PlayCanvas uses CPU skinning to animate these avatars. That can be expensive when too many avatars are rendered. In Uranus tools, we have a script to help mitigate and increase performance with too many avatars. Basically, it's like an animation LOD system. We reduce the playback frequency on distant and non-visible models. We have an example here. Let's take a look. Observe how when the camera zooms in on this character at the center, how the animation is smooth, but from a distance, you can tell that it's missing frames. So that way we can have, 50 characters, and it can render on mobile. That's a big win for social experiences, MMOs, and in general, multiplayer games that use animated models. One very important thing that we did for this demo is use graphics presets, quality presets. So basically, we detect the kind of device that we run on, if it's Android versus iOS versus laptop or desktop, and we scale performance by enabling or disabling some effects. For example, on Android, we definitely disable shadows and post effects. Even with our system, sometimes it's too heavy to run. Of course, we also allow the user to select between these presets because it's super fun to play with this kind of tech demos and see basically what each setting does to the final render quality. A few words about how we did multiplayer. We used Colosseus.io. It's a great system. It's a Node.js multiplayer server that's very easy to get started, and it also includes a free plan to get you started. In Uranus tools, we have a drag and drop relay multiplayer system. That means you can use multiplayer out of the box in your own scenes with no code required, literally. We have a third-person controller that automatically synchronizes with the server. We have a server template written in TypeScript, which is very easy to extend with custom logic for authoritative multiplayer. You can easily get started with this kit to have multiplayer in your own scenes. The way that we do multiplayer is by broadcasting the player state at a set frequency. So the user, the developer, can set how many times per frame he can update this frequency. For example, if it's a competitive game, you may want to do this, let's say, per frame. But if it's just a social experience where you don't really care about accuracy, you can reduce the number of messages you send per second. Sorry, this is not per second. Per frame, this is per second, 10 times per second. 10 times per frame would be too much. In the state, we include only the minimum information required to network this character. In this case, it's the position, the angle on the y-axis. So basically, that's it, where the player looks. And the velocity, which we use to, when we receive it on the client, we interpolate between these different states that we receive to make it look smooth. Everything else, like animations or jumping, is assumed from this stage, so we don't need to network everything. So basically, we don't network animation states like I'm jumping or I'm falling. We just interpret the final position of the character, and the same controller that finds the animations for the local character is run for the remote characters and can understand the right animation state for the player. Here you can see the Colosseum server arena. That's the cloud dashboard where you can upload your server code. And you can, of course, make changes on the fly, deploy. They also have a very cool setting where you can deploy but avoid breaking any games that are run at that exact instance. So basically, the server will wait for the games to finish before pushing the new code updates. Another feature that we have on this scene is using Ready Player Me avatars. These are very cool avatars that come with a full-blown avatar creator, where you can select your character, dress it up, and make it look like yourself. Yeah, exactly like yourself, because you can upload a photo, and they do some facial scanning, and you get the exact model of your face. That's cool. A GLB container is loaded that contains model, materials, and textures. We have a drag and drop script with Uranus Tools SDK that automatically can be used to get a network animated and user control Ready Player Me avatar in your scene with full multiplayer and everything included that you've seen here. Here to the left you can see the avatar creator. That's the default Ready Player Me avatar creator. And to the right the final GLB model animated and exploring the solar stage demo. We also have 3D spatial audio chat in this demo enabled. We use Agora.io. It's a powerful cloud streaming service that allows you to have multi-party audio chat, voice, and also video audio chat. In this demo, we only have voice, but in our SDK, we also support video chat. Agora doesn't really support spatial audio in the JavaScript SDK. Spatial audio is like full-blown 3D stereo audio, like walking around in a 3D scene and listening from your right ear, the player sitting by your side. But we implemented this in Uranus Tools using the browser audio API, using stereo panels based on the real wall position of the player. So you get both mono and stereo spatial audio depending on your choices. This is the script that's being used in Uranus Tools SDK and the full array of settings that you can customize. Now, some metrics about this demo. The demo was literally built in less than a day, from the moment that we exported it from Unreal to the first public build that we pushed. Zero code was written for this demo. Everything was put in place using scripts available in Uranus Tools SDK. So basically, we drag and drop the scripts inside the new PlayCanvas scene. We imported the FBX that we exported from Unreal as GLTF. We set up the scene, we parameterized everything, we tweaked the settings, and yes, we got this build with a file size of less than, I don't know, 20 megabytes, 17 megabytes of download time until the first frame. After the first frame is shown and you start to see the scene, some assets that that have preload set to false are downloaded. So the total download size is 26 megabytes, about 10 to 13 seconds, depending on your network connection. And that's 80 HTTP requests. This is super packed, especially for an Unreal scene. We are very happy with this result. A couple of things about our company. We have Solar Games. We specialize in creating digital worlds for the metaverse. We want to create open worlds with AAA graphics quality, social features, multiplayer inside the web page. We provide services and tools to make this easy. Here you can see some of our demos. All these have been built in PlayCanvas with Ranur's tools. Massive open worlds. This is a Fortnite level size. It's 3 by 3 kilometers. We struggle to push the rendering quality of these scenes. And here you can visit this specific page and view some of our other demos, like our solar pool, solar island, solar supermarket. There are more scenes coming. And enjoy this demo and try our tools on the web right now. We also provide a PlayCanvas mentorship. That's a training program, both for hobby and professional developers, where we do consultancy, training to make you proficient with your goals in PlayCanvas. And thank you for watching. Here are some links for you to reach out to me. This is my Twitter handle. Here you can find more details about our news tools for PlayCanvas. Of course, don't forget to give PlayCanvas a try if this is your first time hearing about this, and connect with the PlayCanvas community. Thank you very much.